All right, so you should have written code that looks something like this. And look how much nicer and easier to read that is than this code here. So, and it actually closely matches the mathematical definition that you could put on it. I said verbally that each Fibonacci number is the sum of the two numbers that comes before it. Mathematically, then I can say fib of n equals fib of n minus 1 plus fib of n minus 2. And that's almost it. If I'm going to write this like I've written the other functions, well, that's true if n is greater than 2. But then we have this stopping condition. If n is 1 or 2, then it's supposed to return 1, right? So the first two numbers in the sequence are 1. If I ask you, well, what are the two numbers before this? There's only 1, so I have to define a stopping condition. So this is our stopping condition. If I don't have this, it's going to go forever. So stopping conditions are very important. Eventually you have to return something that is just a number that's not a recursive evaluation of this function. Okay, so that's how you implement Fibonacci recursively. Let me just compile this and oops, let me just compile this and make sure it works. Oops, Fibonacci. Okay, 1, 1, 2, 3, 5, 8, 13, 21, 34. It looks good. Okay, but the question is this as efficient as the loop? I know that it looks nicer, but does it perform as well as the loop? So I'm going to investigate that experimentally, and I'm also going to compare it to factorial. So let me rewrite this code a little bit to be like factorial, where instead of outputting a sequence, I just input an index in the sequence, so like 5, and it would give me 5, or 7, and it would give me 13. So I'll do something like that. So I'll say, yeah, so the factorial, or the Fibonacci of n is equal to that. Okay. Whoops, I was testing this out before. I already jumped the gun with something. Let me just make sure this compiles real quick. Okay, it's complaining, blah, blah, blah. Okay, sorry, I jumped the gun. But all I've done here is just, I've changed this so that I input a command line argument. So if I say Fibonacci 8, it gives me 21, which that's what I see up here, right? Fibonacci 9 gives me 34. Okay, so now this is back to looking like factorial again. So let me count how many times this function is called. That will be my measure of efficiency. So what I can do is define a global variable. If I define a variable that's outside of any method, it has global scope. Any method can access this variable. So this is a simple way to count things. So every time I call this method, I'm going to add one to the counts. And let me output how long it took. Okay. So I'll do this with Fibonacci first. Sorry, I'll do this with factorial first. So I'll say factorial 6. Okay, that takes 6 steps. So it calls factorial 6 times. And that makes sense, right? You know, first time I take out n, then call the next one, then I keep expanding, right? So that goes through 6 times, you know, just to keep showing you. Factorial 20, which actually is a huge number. It overflows. Let me go for a smaller one. Factorial of 10, okay, this is going to get close to overflowing soon. But it only takes 10 steps to compute that number. Cool. What about Fibonacci? Let's do the same thing with the recursive function. First, we note that the iterative function takes around n steps, right? This loop will go through n times. So the question is, does the recursive version also take about n steps? Does it call itself n times? So I'll do a similar thing where I define a variable int counts, set it equal to 0 initially. Every time this is called, I'll increment that. And also when I output the counts at the end. So let's take a look and see. I would like it if you know, Fibonacci of n only took about n steps. So let's see if that's the case. So Fibonacci of 8. I'm hoping that it's only going to take 8 steps. But it didn't. It actually took 41 steps. Okay. What about Fibonacci of 9? Okay, that actually took 67 steps. Fibonacci of 10, 109. Actually, it's getting worse and worse and worse. It's really pulling away. So let's say I do Fibonacci of 15, for example. Okay, Fibonacci of 15 takes like over 1,000 steps. That's crazy. Fibonacci of 20 takes 13,000. How could that be? The loop would only take about 20. Okay, so I'm going to do a little analysis where I break this down in a flowchart and show you why this is so bad. And then you're going to fix it. Okay, you're going to write a slightly smarter version of this that will avoid this blow up in complexity. To really see the difference between these two recursive functions, let's actually diagram out how they call themselves. So when I do factorial 5, well, factorial 5 calls factorial 4, factorial 4 calls factorial 3, factorial 3 calls factorial 2, and then finally factorial 2 calls factorial of 1, and it stops. Okay, let's look at the Fibonacci function for contrast. So let's say that we wanted the Fibonacci number 5. Okay, so fib of 5 calls fib of 4, then it calls fib of 3. But before it gets to 3, 4 has to finish its job. So then 4 calls 3, and then 2. But then, okay, again, when 4 calls 3, that happens first. So then 3 calls 2 and 1. Now 1's a stopping condition. We don't have to worry about that, but we still have to go through 2 here, which calls 1 and 0, which are each stopping conditions. Okay, now we finish this whole branch here. So we figured out fib of 3 in this part. Now we're going to back up and finish fib of 2. So in this part, so fib of 2 calls fib of 1, then it calls fib of 0, and it's done. Alright, at this point we've computed fib of 3 here, and we've computed fib of 2 here, and so we can finish computing fib of 4. And then, so we're done this entire branch on the left. Now we can figure out fib of 3 over here, and once we're done that, we'll do fib of 5. So we'll do a very similar thing. So fib of 3 over here calls fib of 2 and fib of 1. Okay, but we've got to fill in fib of 2 first. So fib of 2 is fib of 1, which is a stopping condition, and fib of 0, which is a stopping condition. And actually, this is a stopping condition as well. So now we're finished these two, which we can use to finish this, which finally, so we're finished this and we're finished this, we can finish this. Okay, so that was a lot to compute fib of 5. And one thing you notice is, well, we've repeated a lot of work, right? Because when I went to compute fib of 5, I first said, let me do fib of 4. Fib of 4 required computing fib of 3 and fib of 2. And then, we went down this branch here and figured out fib of 3. In the process of doing that, we figured out fib of 2. So why would we want to, if we could remember what fib of 2 was, then we shouldn't have to do this again, right? We can just eliminate this whole branch. Actually, yeah, let me keep that there. So we're going to remember fib of 2, but we don't have to expand fib of 2. We don't have to keep going to the recursion because we already figured it out here. By the same token, by the time I finish computing fib of 4, I've done fib of 3. So I've already done the work of computing fib of 3. So if I can memorize what fib of 3 was when I compute that, I also don't need to expand this whole branch here, which means I can cut out everything below that. So you see that? So with just a little bit of memory, I can cut out this whole big part of the tree down here. And that's going to save us a lot of work. So we just need to come up with a way to remember things.